Alright, so this is our last unit here, and this is actually really the one that everything else we've done up to this point has been leading up to. And so it's actually kind of going to pull everything together. It makes for some, well, from a teacher perspective anyways, good review. Students sometimes don't see the value that I do in that, but it is important. And so we're going to start talking about the idea of a quantitative relationship. Now, when we talk about quantitative, what we mean is we're talking about quantities. We've talked a little bit about quantities when we were in the gases unit, a little bit about quantities when we were in the solutions unit, and now we start to put some of those pieces together. Okay, so the first thing we're going to look at is gravimetric stoichiometry. So let me give you a typical chemistry type question. How do you produce exactly 20 grams of silver? Obviously, you're going to need some kind of starting materials, and normally you'd be given those starting materials. And told you have such and such and such and such, how could you produce exactly 20 grams of it? And so we could look at here is a starting equation, and one of the things to think about is, what does the chemical equation tell us? So here's a balanced equation, and it is indeed producing silver. Now this chemical equation, what you will notice with it is that it has copper as a solid metal. It's got silver as a solid metal as a product. If you had to classify this equation, you would find out that it is indeed single replacement. Okay. And then we could start looking a little bit more deeply at it. One of the things we would see if we start to look a little bit more deeply is that 1 mole of copper, because it's balanced, will react with 2 moles of silver nitrate, of this AgNO3 stuff, and it will produce 2 moles of silver and 1 mole of copper 2 nitrate. Now, we can do a conversion, we've been doing this for quite a while already, between mass and moles, or between moles and mass. And so if I want to figure out that I need 20 grams of silver, we could use silver's molar mass to find out how many moles that is. And we could then look back and say, okay, well, how many moles of copper would I require to get there? From what we've already looked at in terms of ionic dissociation equations, one of the things that you should already be able to figure out by looking at this is, because I've got this 2 in front of here, and in front of the copper there's no number, which means it's a 1. However many moles of silver, we require half that number of moles of copper. Now we're going to get to talking about this, so if at this point I'm talking into a fog of Christmas vacation, we'll come back to that. Anyway, looking at this reaction, it tells us, and these are a few things that perhaps it would be a bad idea to write down. I've talked about them all already. It tells us, and eventually my computer will catch up to where I'm talking, it tells us the type of reaction. So the equation tells us that this is single replacement. So reaction type we can figure out. When balanced, it tells us moles of, let's rephrase that, sorry, relative moles of each reactant and product. So this is where I was saying, if we have 1 mole of copper, it produces 2 moles of silver. Or if we have 2 moles of silver, it's half that number of moles of copper required to get there. Okay. Now, because we know these things, we can do some very important and very useful things. We can start to make predictions. If I know how many moles this is, this 20 grams, I can predict how many moles of copper, how many moles of silver nitrate do I need to get there. That's kind of what this whole last unit is talking about, is looking at chemical reaction equations and then doing something useful with them. So now when we look at a chemical reaction, we do have to ask some practical questions. What do the reactants and products look like? What apparatus is needed to contain the reaction? In the case of this one here, we have solids, we have aqueous stuff, solid and aqueous stuff. So we don't have to worry here about containing gases. What if it's producing gases and we need to contain those? Well, we need a different type of apparatus. As soon as we see gases and we're trying to contain those, we need to have a much more sophisticated apparatus in order to hold on to them. Okay. So how much copper or silver nitrate should be used? Right? If I want 20 grams here, well, how much? Okay, and we sort of talked a little bit about that. The silver nitrate, does it need to be aqueous? Could I use solid copper and solid silver nitrate? Practical question. Will all of the reactants be consumed, or will there be some left over? Do I want there to be anything left over? Well, if I have to pay for the stuff, probably I want to use up as much of them as I can. Should there be any left over? This is an important one. How long will it take? Another important one, safety-wise, will it be endothermic or exothermic? Is the process of doing this reaction going to generate enough heat to melt my apparatus? Is it going to freeze the liquid it's in? All of these are important questions we need to ask. Oops. Could the products of this reaction be achieved through another method? And if you're a chemical engineer, which is actually what a lot of these questions are sort of geared towards, is that other method cheaper? Okay. And then finally we could ask ourselves how much of the products should be expected. So, a couple things first of all that chemical reactions do not describe. They do not describe the pressure and temperature. Unless otherwise told, we have to assume SATP, standard ambient temperature and pressure. That has to be specified, but it is not specified in this equation. This doesn't tell us a thing about temperature and pressure. We might write it next to this, but this doesn't tell us temperature and pressure. Process. The reaction does not tell us about the process. It paints a before and after process. What happens during the reaction? Were there any intermediary steps? Maybe it starts off as a clear liquid, it turns purple, then it turns blue, then it turns red, green, yellow, and finally settles on blue. We don't know. That's not told to us. The process isn't told to us. The progress doesn't tell us how long. Doesn't tell us if it reacts completely. Okay. Measurable quantities. It doesn't tell us anything about mass or liters or molarity. And I think, whoa, Mr. Parker, you just said it tells us about moles. I qualified that word. Relative moles of each. I said that on purpose. For every 1 mole of copper, you produce 2 moles. It doesn't say that you have to have 1 mole of copper or the reaction doesn't work. Okay. The chemical reaction does not describe a specific mass. Now, I can write underneath here that I want to get 20 grams, and I can use this to predict how many grams I'd need to get there. But again, this reaction equation is just a tool. Now, we have to assume a few things when we write them. We assume that they're spontaneous. Okay, I guess, what if they don't react? What if they require a catalyst? We have to assume that the reactions are fast. Okay, I can write this equation right here. Iron plus oxygen and it's going to give us a bunch of products, but I'm going to care about one of them. It's going to make iron 2 oxide. And we need 2 in front of that. I saw this reaction over the holidays. My son had a birthday party. We put little sparklers on his cupcakes. Guess what? That reaction happened. If any of you have ever looked at the bumper or the fender of an old vehicle, you'll have seen evidence that this reaction has happened. But you probably have never seen a car rusting. Combustion of iron in the sparkler is fast. Rust is really slow. That reaction that's on the screen there, it doesn't tell you if it's fast or slow. Okay. We assume when we're doing these things that the reaction is fast. Okay. It may not be, but this reaction doesn't tell me anything about the speed. We assume that they're fast. That when we mix stuff together, that something actually happens right away. We have to assume that the reactions are quantitative. That when I write a reaction like this, that actually happens. Like, 99% of all the copper reacts with 99% of all the silver nitrate. Okay? Now, when you get to Chem 30, you're going to start talking about non-quantitative reactions. Okay? We assume here that it's more than 99% complete and that all of the reactants have been used up. Okay? We also have to assume that the reactions are stoichiometric, which means essentially that the equation coefficients don't change over time. That only one reaction occurs at once. Okay? So we have to assume that this is true, that 1 mole of copper will react with 2 moles of silver nitrate to produce 2 moles of silver and 1 mole of copper 2 nitrate. That over time this doesn't somehow change. Okay? Now, background here. Some reactions will only occur in water. Okay? Sometimes dissolving a reactant into its ion is required for a reaction to proceed. So we can look at, for this, dissociation, that's an ionic compound dissolving in water, or ionization equations. This is an acid reacting with water. Now, looking at that, sometimes it is hard to tell whether a solution has undergone a chemical change because there are a lot of colorless solutions. Often there are ions in solution. They're not part of the reaction. They're along for the ride. We need them in order to get the reactable, new word for the day, reactable substances there. Okay, so for example, when we look back at this equation that I've been beating to death, we have silver nitrate and copper 2 nitrate. All of the nitrate stuff, it's aqueous before, it's aqueous after. It's not reacting. It's along for the ride. Now, in order to get silver ions to the party, they've got to come with somebody. This is sort of like the, bodyguard who shows up but doesn't do anything. He's just standing there watching, or the chauffeur. Okay, he comes to the dance, drives silver to the dance, apparently drives copper home from the dance, but he's not actually doing anything. He's not dancing. Okay. Ions like that are called spectator ions. Okay. So here's another example. If I take silver nitrate and sodium chloride, mix them together, okay, I'm going to get settle down there, a bunch of ions. Okay, right? The silver nitrate will dissociate and it's going to form silver ions and nitrate ions. Silver ions and nitrate ions. There they all are floating around. I dissolve my sodium chloride. I'm going to get sodium ions. There they are. And chloride ions. When I mix them together, the chloride and the silver, if you look at your solubility table, so you can get that out, the chloride ions and the silver are very attracted to each other, and they precipitate out of solution. And so we're left with, at the bottom of the beaker, a white solid. Well, it turns out to be white in this case. It could be other colors depending on the product. This is a very insoluble substance, silver chloride, but we're also left with, now we write it down as sodium nitrate, but if we look at it, what it is in solution, take a look. Sodium nitrate. Well, what's been floating around here? Oh, there was sodium floating around here. Sodium floating around here. And nitrate floating around over here. Floating around over here. It's still floating around. Right? It's doing nothing. It's just sitting there. Sort of like my cursor here. What we've got is a spectator, actually two spectators. We have sodium ions and we have nitrate ions. They're just there watching. They're called spectator ions. Now, if we write an equation and we leave out any entities that don't actually react or take place in the reaction, we call this the net ionic reaction. To do this, we need to dissociate or ionize any applicable reagents. So, we can write out this is our ionic equation. Okay, our chemical equation. Okay, it shows all the ions, it shows all of, this is our chemical equation. Let me rephrase. Then if I want to go to a net ionic equation, I have to figure out first of all, okay, copper 2 sulfate, that's aqueous, that's dissociated. And so what I actually have here is I have zinc as a solid. You should be writing this down. I've got copper 2 sulfate, which has formed copper 2 plus ions. They're aqueous. You need to write the subscripts that, in fact, these are aqueous things. Sulfate, so 4,2 minus. This is forming copper solid. Now I can tell you I know this reaction is balanced. If it's not balanced when you start, this whole process just takes us a bit longer, and so I'd recommend balancing it before you start. Plus, okay, zinc sulfate, that's aqueous. Okay, that's going to be Zn2 plus. Aqueous. And SO4 2 minus. Let's make those actually look like numbers. And now we need to look at, if we're trying to write a net ionic equation anyways, is there anything that's the same on both sides? In fact, yes. Sulfate is here, sulfate is here. It is a spectator. So if I want to write the net ionic reaction, I write everything that I've got here except for the sulfates. I'm showing what's actually involved in the reactant. Okay, I have zinc solid plus copper 2 plus. So this is not showing everything that is present. It's only showing the stuff that's changing. I have zinc solid and I have copper 2 plus. That's changing to copper solid. And zinc 2 plus. Which is aqueous. This is why it's important to write the ion charges and write the states. Otherwise, zinc plus copper gives me copper plus zinc is a meaningless statement. Once I include states of matter, it becomes useful. Alright. So, gravimetric stoichiometry, with that as our basis, it comes from the Greek meaning basically measuring elements. What we're going to be doing with gravimetric stoichiometry is we're going to be doing calculations of quantities in chemical reactions based on a balanced equation. There's two basic types of problems: mole to mole or mass to mass. Mole to mole is probably the easier of the two types. Mass to mass is not any more difficult, it's a little bit more time consuming because we have generally two extra steps that we have to go through. Okay. So looking at this, how many moles of oxygen are produced when 3.34 moles of Al2O3 decompose according to the unbalanced equation given here? There's our hint. Hey, we should probably balance this thing. Okay, so I'm going to write it out big enough so that you can actually see it. So we have Al2O3 solid. What we're going to do with this, I should do the work here first. Let's not worry about that. So solid aluminum, leaving room in front of both of these to write coefficients. O2. Now look here and I say I've got 2 oxygens and I've got 3 oxygens. This is an odd number, this is an even number. I'm going to have to multiply this side here to make it an even number. So let's put a 2 here. Now I've got a grand total of 6 oxygens. Okay, and so I'm like, okay, what times 2 get? Oh, I need a 3 here, and I need a 4 here. Now, the way I always do these problems is I'm going to start out by writing my quantity underneath whatever it belongs to. Say, okay, little n is equal to 3.34 moles. Then I start and I look and say, okay, I want to get moles of oxygen. And so I'll write n is equal to question mark. Now what we're going to do next looks very similar to what we've been doing already when we were doing the dissociation of the ions to find concentration of ions in solutions. Okay, so I'm going to say, okay, number of moles, I want N of O2. I want to find the number of moles of oxygen. It's equal to, first thing I write is what I have. I have 3.34 moles of Al2O3. I'm going to multiply it by the mole ratio. Multiply it by, put it as a fraction, moles of what I want. I have 3, according to the equation, there are 3 moles of oxygen for every 2 moles of Al2O3. Right. Looking over here, hey look, units. Moles of Al2O3, They cancel. I'm left with moles of oxygen. Now I just need to do the multiplication. And so I have 3.34 moles, well, the number 3.34, times 3. And I've got to divide everything by 2. And this is going to be, once I've done the multiplication, my number of moles of oxygen is going to equal 5.01 moles. Again, we've done this same type of a thing already. So this is just applying the same skill that you've already learned in a new situation. Okay? Moving along. Here's another one. Okay? Alright, so with this here, once again, we need to deal with balancing the equation first. So we look and say, okay, balance this. Oh, hydrocarbon combustion. Start thinking, okay, how do I balance hydrocarbon combustion? Well, balance the hydrogens first. 2 here, 2 here. Hey, that looks good. Oh, wait. If I have 2 over here, it means I've got 1 oxygen. That's an odd number. That's not going to work. So I need 2 of these, which means I need... Now I've got 4 hydrogens, so I put 2 here. Now I've got an even number of oxygens. That makes me happy. I've got 4 carbons, so I need 4 CO2s. And now I've got a grand total of 8 plus 2 is 10 oxygen atoms, so I need a 5 here. Okay, so if 3.84 moles of C2H2 are burned, how many moles of oxygen are needed? So given 3.84 moles of C2H2 times my mole ratio of 5 moles of oxygen, five moles of O2 for every 2 moles C2H2. See, balancing the equation is very important. If you can't balance the equation properly, your answer here is going to be wrong. We do the multiplication there, 3.84 moles of C2H2, 4 times 5 divided by 2. And this is equal to 9.6 moles of oxygen. And look at this going the other direction as well. How many moles of C2H2 are needed to produce 8.95 moles of H2O? So, okay, I've got 8.95 moles of H2O times 2 moles of C2H2 per 2 moles of H2O. And you should be able to see at this point, oh yes, if I'm looking to produce 8.95 moles of H2O, guess what? I need, well, I can do times 2 divided by 2. I think all of you are at the point you can realize that this is the same as just times 1, that we need 8.95 moles of C2H2. If 2.47 moles of C2H2 are burned, how many moles of CO2 are formed? Okay, so again, multiply this by what I want. That's moles of CO2, so 4 moles of CO2. What I want over what I have over per 2 moles of C2H2. We've got 2.47 times 4 divided by 2, and it's going to produce 4.94 moles of CO2. So once you have a balanced equation, mole-to-mole stoichiometry is pretty easy. You just need to look at the mole ratio, the ratio of what you want over what you have. Okay. Now, we don't have a good way to measure moles. Now, a mole is 6.02 times 10 to the 23rd molecules. If you were to count that, okay, it would take you a long time, and counting a mole of one thing would be more than you'd be able to do in a typical lifetime. As an aside, you could calculate how many seconds there are in say 80-year lifespan of somebody, and if you counted 1 per second, you could figure out how many moles you could get to, or how many molecules you could get to, and you'd find it would be significantly less than 1 mole of seconds that you would live in 80 years. So that being said, we can convert grams to moles. Okay, you use your periodic table and the molar mass. We've been doing this kind of thing already. Now we can convert moles of one entity to moles of another. And this is what we were just doing up here using the coefficients. Okay. So if we're, and this is kind of the process we use. If we're given grams of substance A, we use the molar mass of A to find the moles of A. We use the mole ratio, the coefficients of A and B, to find moles of substance B. We use the molar mass of substance B to find the grams of substance B. We're going to add to this little U-shaped thing over time. We could have, and if we're doing solution stoichiometry, we could have concentration and volume of substance A to find the moles of substance A. Okay, we could use gas laws here. Okay, where I have the volume of a gas at a certain pressure and volume, so pressure and temperature. Let's try that again, and I can use that to find moles. Okay, but for starters, grams. Use the molar mass to find moles, coefficients to determine moles, to go to molar mass to find grams. Okay, let's look at how this works actually. Okay, so I've got an unbalanced, and typically you get an unbalanced equation, so deal with it. And we're going to figure out what we have to do here. Okay, so I look at this and I say, okay, let's balance this thing before we do anything, really. And so I've got 2 irons on the right-hand side, and 2 needs to go over here. And then I've got, let's see here, 1 copper on both sides. That looks good, but oh, SO4. I've got 3 SO4s here and only 1 over here, so I'm going to multiply this by 3. Which means I need a 3 in front of this one, and then everything's happy. Okay. So, if 10.1 grams of iron are added to a solution of copper 2 sulfate, how many grams of copper would form according to the following unbalanced equation? So, again, I start by writing out, scroll down too far, what I know. Mass of iron is equal to 10.1 grams. All right. Now, 2 ways we can do this. I'm going to show both of them. One is, they both do the same thing. One is where we have one big equation, the other is where we use several shorter equations. Okay, so here we go. No matter which way I do this, though, I need to find molar mass of both iron and copper. Now, in this case, that's nice and easy because I can just look on the periodic table. I don't have to add anything up. So my molar mass of iron, once I look on my periodic table, here it is, 55.85 grams per mole. Write out the units. Right. I am looking for the mass of copper. I can figure out the molar mass of copper by looking at my periodic table. Come on, there we go. And it's on this page, 63.55. Grams per mole. Alright, so very first thing I want to do here, this is method number 1. Okay, using formulas. I'm going to find out how many moles of iron I have. N is equal to little m over big M. Is equal to 10.1 grams. Per 55.85 grams per mole. And it's equal to, do not round your answer to this, 10.1 divided by 55.85. Keep the big number in your calculator. I can write down, I'm going to write down just 0.18 ... moles. The ... is on the paper to show that yes, I am keeping the big number and I just don't want to write down 10 digits on my sheet of paper. So now I'm looking essentially at a mole to mole kind of question. I have 0.18 moles of iron. How many moles of copper will be formed? Okay, so my moles of copper. Start writing this underneath the copper. So number of moles of copper is going to equal this number here, 0.18 moles. 0.18 ... moles of iron times what I want, 3 moles of copper. I'm running out of space. For every 2 moles of iron. Getting those numbers, of course, from my balanced equation. Guess what? Moles of iron go away. I'm left with moles of copper. So I've got my big number left in my calculator. And this is going to form 0.27. Again, I'm not rounding until I get to the very last step. 27126323098 and so on. 27 ... moles. Well, now I want to figure out the mass. I have moles and I have molar mass. Mass is equal to moles times molar mass. I'm shy on space. On the screen, I'm going to take this number and multiply it by this number. This one is my N, this one is my M. I multiply them together, so the number in my calculator times 63.55, and I should form 17, and now I got to figure out 3 significant digits, 17.2 grams. That's method number 1. Okay, I have in method number 1, 1, 2, 3 equations that I'm using. Okay, method number 2. Write everything down into one equation. The math I do is identical. I still need to find out the molar mass of both of them. Now again, for this one, that's pretty straightforward. Now in this case, I write out, okay, I want to find out the mass of copper. I write down what I want to know. And then I start by writing down what I have. Okay, 10.1 grams of iron. Now my first step is I want to change that into moles, right? If I go back up to here, I want to change to moles of substance A. Okay, so I'm going to say times 1 mole of iron per 55.85 grams of iron. Now sometimes people look at this and go, whoa, 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 whoa. Molar mass is grams per mole. That's absolutely right. This is grams per 1 mole, which means that 1 mole has a mass of 55.85 grams. And so I can just as easily say 55.85 grams per 1 mole as I can say 1 mole per 55.85 grams. Okay. So now I've got, okay, grams of iron cancel. I've got moles of iron. Okay, what do I need next? Okay, I need to go from moles of substance A, which in this case is iron, to moles of substance B, that's copper. Okay. So multiplied by, I want to have copper. So say, okay, so I've got 3 moles of copper. For every 2 moles of iron. Okay, so again, grams of iron have gone away. Moles of iron have gone away. I've got moles of copper now, and I need to go from moles of copper into grams of copper. So, just to distinguish this, I'm going to multiply this now by, okay, I've got moles, and so I want to get grams. So I have 60, what I want, 63.55 grams of copper divided per every 1.1 mole of copper. Moles are top, bottom, they go away. And now, that's what I want. I want grams of copper. So how do I go about doing this? Okay, well, first of all, just to kind of review what I've done. Each step of the way, I've written these conversion factors, these fractions here, where I put on the top what I want to get to, over on the bottom what I have. Okay, and I'm using this idea here. I have grams of substance A. I want to go to moles. So it's grams on top, moles on bottom. Now I've got moles of A. I want to get to moles of B. So I put moles of B on top, moles of A on the bottom. And then I'm going to multiply by molar mass. Okay, I want to go to grams of B, so I need grams on top and moles on bottom. Exactly what I've done right in here. So now my mass of copper is going to be equal to, take everything on the top and multiply them straight across. So I've got 10.1 times 1 times 3 times 63.55. Do that in one step. So 10.1 times 1 times 3 times 63.55 equals. Lovely. And now, 2 ways you can do this. I'll tell you the way that I always do it. You can use brackets if you want. I divide by the first number in the bottom, so divided by 55.85. Press enter. And now I divide by 2. Divide by 2. And I end up with 17.2 grams. Same answer. If I would like to divide by 1, I can do that as well, but I can do that math in my head. Dividing by 1 just gives